Hi, I'm Myeongjin, and I also go by Bruce. I'm an undergraduate student at KAIST, and in this summer, I am researching at Caltech under Professor John Praskill and also Professor Yu Tang. So I'm going to give a talk about certifying and learning local quantum Hamiltonians, which is a contributed talk in TQC. So if anybody's coming to TQC, please let me know. So yeah, let's begin. This work was done by those wonderful people and me, and you can see Junzo, who is currently in here. So yeah, this work was done by a lot of people because it was merged by two papers. It was originally there were two papers, and we submitted to TQC as one work. So yeah, in this talk, there's gonna be a lot of some informations and some theorems. So I try to make it not complicated as possible. So yeah. So let me start. So as said, we're going to certify and learn a Hamiltonian. So first, we should know what is a Hamiltonian in this setting. So as you know, a Hamiltonian is a rule of some quantum system. And this Hamiltonian is usually used and described by the Schrödinger system, and they can also describe the quantum system. So in an operation sense, the Hamiltonian H is a generator of a continuous time quantum gate, which is expressed as e to the minus iT. We sometimes call this as a time evolution operator, and we can query to this time evolution operator and try to learn or certify the H. And another setting is the thermal equilibrium state, which is also called as the Gibbs state, which is represented like this. And we are given identical copies of this Gibbs state, and we try to certify or learn the Hamiltonian H or the Gibbs state itself. So as said, the first setting is trying to learn or certify the Hamiltonian H in the dynamics model, which we can give queries to e to the minus iT. Giving queries to e to the minus iT can give information about H, so we can extract some information, and that's the main goal of this talk, trying to extract the information of H by querying to e to the minus iT. And another setting is querying, not querying, just doing some measurements to the Gibbs state. Yeah, the Gibbs state is defined like this, which the beta is the inverse temperature of the quantum system. So if we know H, we can know the Gibbs state. But inversely, even if we have the Gibbs state, it is quite hard to know H. So I will explain the details later. But the thing to remember in this slide is that we are going to learn and certify the Hamiltonian H in those two settings, the dynamics model and the Gibbs state model. Yeah. So, and another thing to emphasize is that as the title in this talk, we're going to certify and learn local Hamiltonians. So we need to know what is local. So I'm going to define what the locality of Hamiltonian is. The Hamiltonian can be written as a sum of Pauli string terms as this. H can be represented as the sum of HP, which is the Pauli coefficient, and P is the Pauli operators, which can be expressed with the single qubit Pauli terms I, X, Y, Z, and can generalize it into n qubits. And the Hamiltonian can be represented as the sum of those Pauli terms. Then what do we mean by local? Let's just look at the single Pauli term. If the Pauli term is represented as Z3 and Z7, then it is called two locals. A term is k-local when it only touches at most k qubits. As you can see, another example is x1, y4, z5, which means that x is applied on qubit 1 and y is applied on qubit 4 and z is applied on qubit 5. This is 3 local. So we define the locality of the Hamiltonian as the maximum locality of the of its Pauli terms. Yeah. So we can define the locality of the Hamiltonians like this. And we are going to look at local Hamiltonians, which means by that the locality of the Hamiltonians is constant. So yeah, we should remember that in this talk, we are going to look at the Hamiltonians which the locality is constant. And this is not used in this talk, but just for reference, we can also define the sparsity of the Hamiltonians, which is the non-zero number of the non-zero terms in the Hamiltonian, non-zero Pauli terms in the Hamiltonian. Just for reference, this is the sparsity of the Hamiltonians. Yeah, so let's get back to our work. As said, we're going to do 2 tasks in 2 different data models. First, we're going to learn which in 2 models. The first is the dynamics model, as I said. We're going to learn the h by querying to the e to the minus IST for various t's. And for the Gibbs state model, we kind of avoid learning the direct h. We try to directly learn the Gibbs state. I'm going to explain the reason later, but it could be some weak result, but learning directly the Hamiltonian cost exponential number of samples, so we just avoid it and try to learn the Gibbs state itself. And in certification, also the dynamics model, we query to e to the minus IST for various t's and test whether h and h0 are close or far. And in the Gibbs state model, we also test whether the Gibbs states are close or far. So first, let me more explain about the dynamics model, which is also called as the real-time access model. As said, we may choose the waiting time t and apply this operator. So we can prepare some initial state and apply this e to the minus IST with some control. I will explain what is a control in this Hamiltonian learning task and then measure. We're going to learn h with the infinite Pauli norm and certify the Hamiltonian with the normalized Frobenius norm, which I will explain it later. So what do we mean by control? And how are we going to tell whether we learn the Hamiltonian efficiently or not? So I'm going to explain what is control in those Hamiltonian learning or certification tasks and explain about the cost. So in one experiment of the dynamics model of the Hamiltonian, we can use several queries to the dynamics. So we can prepare a state and then apply the evolution e to the minus IH T1, then apply a known unitary, which is called as control V1, and then apply the time evolution, then apply the known unitary V2, and repeat this procedure, and then do some measurements. We do this experiments in the real-time dynamics model and try to learn the h or certify the h. So then what are the costs? The main costs that are considered in those Hamiltonian tasks is the total evolution. We need to make it small as possible. So the total evolution time is defined as the sum of all the evolved time used in the experiments on on all of the experiments. So you can see that we can just sum up the TJs, which are the evolution time used in every evolution. Yeah. So this is the total evolution time, and almost every Hamiltonian work or papers try to make this total evolution time as the Heisenberg limit, which is trying to make the total evolution time 1 over epsilon, where epsilon is the desired accuracy. And another important cost is the number of queries that are used and the number of repeated experiments and the minimum resolution time, which is the minimum between the TJs and the classical post-processing time. In my opinion, the second important thing is the minimum resolution time. And the thing that needs to be required is to keep the number of queries and the classical post-processing time as polynomial, not exponential. And I personally think that number of repeated experiments is not that important, but yeah, some works try to reduce that also, so it could be important, but the main thing is the total evolution time, so we are going to focus on that. And let's look at the Gibbs state model also. Yeah. In this thermal model, as said, we are not going to control the time evolution, but we are going to receive many identical copies of the Gibbs state. So we can measure each copy once, and also in this work, we just use simple Pauli measurements. And here, beta is the inverse temperature of the system. So larger beta means lower temperature. So what are the costs? Yeah, of course, the cost is just the copy complexity. And sometimes it could be important to consider the classical post-processing time. But the main cost is the number of copies measured. And yeah, learning uses the copies of rho h beta, which is the Gibbs state of the system, and certification uses in our work. Certification uses copies of both the original Gibbs state and the target Gibbs state. Yeah, I'm going to explain it later. And for those Gibbs states, the distance measure that we use is the trace norm. So I'm going to explain the results first, and then explain the main algorithm and the methods. So as said, in the real-time access model, the dynamics model, the cost is the total evolution time. Previously, the best total evolution time of learning the Hamiltonian by the dynamics model is O S over epsilon. My personal thoughts, and most of the people researching Hamiltonian learning think that it is optimal, but it is not proved. So in this work, we don't improve it because we think that it is optimal. But it could be cool to prove the lower bound. But yeah, to my best knowledge, that there is no lower bound yet. And the thing that we improved is the certification. The previous best certification was S to the 3 over 2 over epsilon, or 1 over epsilon to the square. Here, S is the sparsity. So for k-local Hamiltonians, there were no efficient Heisenberg limit algorithms, but we found an efficient Hamiltonian certification algorithm for local Hamiltonians. So in this work, we improved the total evolution time as O c to the k over epsilon, where c is a constant. So for a constant locality where k is a constant, this total evolution time cost is 1 over epsilon. And it is known to be optimal. So we found an optimal certification algorithm for Hamiltonians for the constant locality. So this is one of our main results. And for more previous results, it was known that two local Hamiltonians can be certified within the Heisenberg limit total evolution time, but there was no algorithms for certifying the Hamiltonians in the Heisenberg limit for general K local Hamiltonians. So this was the first result of generalizing that two local Hamiltonian result. So this was the motivation, trying to generalize the above result for which K is bigger than 2. And in the Gibbs state model, prior works try to learn the Hamiltonian from the Gibbs state model, but it is proven that it costs exponential number of samples. So we try to research in a different direction. We try to learn and certify the Gibbs state itself. And in this work, trying to learn the Gibbs state only costs polynomial number of samples, but inefficient time complexity. But certification only costs about polynomial samples, and it is time efficient. This was the difference in our results. So now I'm going to explain about our methods and some algorithms and some key ideas. So formally, we got this theorem. For constant local Hamiltonians, we can certify the Hamiltonians by total evolution time 1/epsilon, which is optimal, by using access to the real evolution time. We don't need any control time evolution or inverse time evolution. So we can argue that our work is practical in the real setting, because using control time evolution or real time evolution is not that relevant in the physical sense. And there were some works that achieved 1/epsilon by using some control and some inverse time evolution, but we only use the real time evolution. What I mean by real time evolution is using only queries to e to the minus IST, where t is a positive time. Using negative time or some control unitary operation over e to the minus IST is not that practical, so we try to avoid it. So we proved the upper bound, and the lower bound simply comes from this example. It was known, so we achieved optimal constant local Hamiltonian certification. And I just wrote the definition of that Frobenius norm H. The Hamiltonian certification is usually done in the Frobenius norm. So just might notice that it is the squared sum of the Pauli coefficient of the matrix, and then we can just root it, and that's the Frobenius norm. We should remember it for the later slides. So as you can see, we did tolerant certification. As you can see, we can determine whether the H and H0 is close or far. But just for simple explanation, in this talk, we're going to discriminate the two cases where H and H0 are equivalent or it is far. Just for simplicity, I'm going to explain about intolerant certification. So first, let's define delta H as the difference of H and H0. So if they're same, of course, delta H is going to be 0. And if they're not same, h minus h0's Frobenius norm will be bigger or equal to epsilon. We are going to discriminate those two cases. So we are going to use Bell sampling on e to the minus it delta h, but it is not that trivial that we can query to e to the minus it delta h, because in the dynamics model, we only assume that we can query to e to the minus ht, not to the e to the minus I delta ht. Even though we know h0, it is not that trivial that we can query to, to the time evolution of delta h. So, but fortunately, there's some product formula that we can do. It is called totalization. And by using this product formula, which is called a totalization, by knowing the target h0 and by having the ability to query to e to the minus iht, we can query to e to the minus I delta ht approximately. We can approximate it, yeah. So we now on we will just assume that we can query to the time evolution of delta h. So as said, we're going to Bell sample to e to the minus it delta h. I assume that people here all know about Bell sampling, but just for explanation, we are going to prepare n qubits and some ancilla n qubits, and we're going to prepare the Bell states, and then by applying the unitary u on the top of the n qubits, and then measuring by the Bell basis, we can get the Pauli coefficients of the unitary matrix u. This is Bell sampling. And in this work, we are going to, the important quantity is the Bell sampled outcome of the identity probability, which is the coefficient in front of the identity I when we represent the unitary u as the Pauli basis. So this identity probability is the most important quantity of this work when certifying the Hamiltonians. So we're going to Bell sample because of this intuition. So as you can see, if h and h0 are the same, then of course delta h is 0, and e to the minus it delta h is an identity. So if we Bell sample from this unitary, we will always get the identity. But if h and h0 are different and therefore sometimes there will be non-identity Pauli operators when we Bell sample from that unitary operator. So yeah, this is the reason we are going to Bell sample it. And now we need to prove that this works. So yeah, now we're going to prove it. So as said, Bell sampling is just trying to get the Pauli coefficient of a unitary. And it is actually known in this paper by Yutong that by Bell sampling from this time evolution operator of the delta h are represented like this. The probability of getting the identity element from the Bell sampling procedure are represented like this, where the lambda 1 through lambda n are the eigenvalues of the delta h, and then the probability are represented like this, with some cosine, with some t, with some eigenvalues of the delta h. Yeah, we should remember this. Yeah.
Sorry, can I quickly ask a small question?
Yes, of course.
So here, this delta H, you're not probably making any assumptions about it, right? In the lemma, I guess the lemma holds for any delta H, or does
Yeah,
it have constraints? Okay.
yeah. We're only going to use the assumption on the locality in the later part. Yeah.
Right.
Yeah.
Makes sense. Okay, thanks.
Yeah. This lemma's proof is not that hard. Yeah. So yeah, we can just simply use some basic mathematics. So yeah, I will just move on. But we can get a very important intuition from this formula. So as said, our goal is to discriminate and prove that if H and H0 are far from each other, then the non-identity element from the Bell sampling procedure will happen with high probability. Yeah, that's the thing we want to prove. So we want to prove that if delta H, so if the Frobenius norm of delta H is bigger than epsilon, then this IT, this probability of getting the identity, should be smaller than 1 with some amount that we can discriminate. Yeah. Then how should it be? Then we should have, as you can see, this is the average of cosine, the difference between the eigenvalues multiplied by some t. So if the difference between the eigenvalues are always 0, which is the case when delta H is 0, this will be 1, always 1. The probability will be always 1. So we need many eigenvalues that are different, and the difference should be big. So yeah, as said, our goal is to achieve the Heisenberg limit. So we can only increase t to the magnitude of 1 over epsilon. So in order to make this term far from 1, we need to increase the t, but also this difference of the eigenvalues need to be large. So I'm going to explain the intuition in this slide. So we have the cosine graph, and near 0, if the difference of the eigenvalues are near 0, then every term will be close to 1. But thankfully, we can increase this difference by multiplying t, by increasing t. Then by increasing t, we can redistribute those dots on the cosine plane and make it like this. Then those dots are, as you can see, those dots are far from 1. So we can make the probability less than 1. But those difference at least have to be bigger than some magnitude, because we can only increase t by the magnitude of 1 over epsilon. So we're going to prove that there are sufficient number of different eigenvalues in this setting. Yeah, that's the goal we are going to prove. So we are going to redefine this quantity, the proportion of epsilon for eigenvalue pairs. So for an Hermitian matrix X, we're going to define this lambda quantity, which are the proportion of the epsilon for eigenvalue pairs. Yeah. Now you will get the intuition why this is important. Yeah. So we just have to prove that this quantity is bigger than some constant. The reason for that is we have this lemma. More formally, if that proportion quantity is bigger than some constant d, then we have that for randomized random selection of t, we can get the guarantee that the probability of sampling the identity element from the Bell sampling is always less than 1 by this difference, d over 4. So if we get a guarantee that this lambda quantity is bigger than some constant, we can discriminate the equal case and the forward case by only bell sampling constant times, because the difference from 1 is some constant, so we only need to do the bell sampling procedure constant times. And since t is in 0 to 2 over epsilon, it only costs the Heisenberg limit, so we can certify the Hamiltonians by using the total evolution time on the magnitude of 1 over epsilon. So yeah, by this lemma, the only thing left is to prove that this lambda h comma epsilon is bigger than some constant. Yeah, this is the only thing left. Any questions?
Yeah, sorry, I have a basic question. So, how do you prove this? So, if you can give some intuition. So, from what I understand, you do a time averaging of the Hamiltonian evolution, right? 1 over t, 0 to integral 0 to t, e to the minus I, delta h, and then you diagonalize e to the minus I delta h, and then write it in terms of like the inverse of the eigenvalues, right? Inverse of the eigenvalue gaps. So what else do you do? So this is like how I would approach it. So how do you prove this? Can you give me some intuition about this?
About this lemma?
Yeah.
This lemma. Maybe it is better to directly see the paper, but the intuition is we can just use some probability bounds. And as you said, yeah, we can use some integrals, and by using some probability bounds, we can prove it simply. It's not that hard, so maybe it would be better to look at the paper.
Okay,
yeah.
Sure.
Yeah. Thanks for the question. And yeah, now just remember that our goal is to prove that this lambda quantity is bigger than some constant. And just for spoiler, this constant is going to be something like 9 to the minus k, where the k is the constant. So that's the reason why the locality needs to be a constant. Yeah. So if the k is 01, then yeah, 9 to the minus k will be a constant. And so yeah, we can certify the Hamiltonians in the Heisenberg limit. So we're going to prove that. Yeah. So yeah, as said, we are just doing the intolerant case. So, and just for simplicity, now we have a guarantee that we can just apply e to the minus delta ht. We're just gonna represent the delta h as h. It's not that important to represent delta h or h. So just for simplicity, we're going to express it as h. So our goal is to prove this. When the Frobenius norm of h is bigger or equal to epsilon, we need to prove that this quantity is bounded by some constant. So how are we going to do this? Let's recall the definition. This definition of this quantity is the proportion of the epsilon for eigenvalue pairs. So what is it? Yeah, it's the proportion of some distribution of the tail. So if we represent the difference of the eigenvalues as some distribution, then we can say we want to calculate the proportion of the which the values are bigger or equal to epsilon in the distribution. So by this intuition, we can use some inequality that is known. We can use the Pauli-Zygmunt inequality, which low bounds the deep in the right tail. Yeah. Our goal is to low bound the quantity lambda, and the lambda can be dot as a distribution. So this fit well. So we can use this Pauli-Zygmunt inequality, which I will call as PZ inequality. So as said, let's just make it as a distribution. Let's just define some random variable as f s comma t, where s and t are the variables, as hs minus lambda s minus lambda t, which is the difference of the eigenvalues. And since the PZ inequality requires the random variable to be a positive variable, we're going to define a y as the square of f. Yeah, so if we do that, we can use the PZ inequality, and the PZ inequality is represented like this. For if we just set zeta as 1/2, the probability of y becoming greater or equal to the average of y times 1/2 is lower bounded by this representation. Yeah, it is well known. And so what should we do? As you can see on the right side, now we need to compute the second moment and the fourth moment of f. This is because y is defined as square of f, and as you can see, there's the first moment and the second moment of y, and yeah, since y is the square of f, we need to calculate the second and the fourth moments of f, which is the difference of the eigenvalues. So by using simple calculations, remember that f is the difference of the eigenvalues, and just by squaring them and averaging them, we can get this result that it's 2 times the Frobenius norm of the matrix and then squaring it. Yeah. And the fourth moment, using some simple calculations, we can get this. Then what should we do? We want to bound this quantity, low bound this quantity. So we need to have relations between the fourth moment and the second moment. So in order to get a relation between this fourth moment and the second moment, we need to have a relation between the norm of the delta H. So is there a relation? Yeah, thankfully there's a relation called hypercontractivity, which is the Bonami lemma in the quantum setting. If on Hamiltonian H is k local, this is where the locality comes from. Yeah, this is the reason why the locality is important in our work. If the Hamiltonian is guaranteed to be k local and it's on n qubits, which doesn't matter, it holds that the p norm of the Hamiltonian H is upper bounded by the 2 norm, which is the Frobenius norm of H, and some constant p minus 1 to k/2. Yeah. So since we can just directly apply this theorem and get that delta H, the 4 norm of delta H is upper bounded by the second norm by this relation. So we assume that H and H0 are all k local, so delta H is also k local. So yeah, we can apply this theorem. And since we have this norm relations, we can just apply this to this calculation of the second and the fourth moment, and we can have this. result. Yeah, we can have this result, and by applying this inequality directly to the PG inequality, we have this low bound. Finally, we have this low bound. Yeah, we can just directly apply this. And as you can see, this probability of getting the difference of the eigenvalues, which is f, bigger than the Frobenius norm of delta h, which we assume that delta h and h0 are 4, epsilon 4, so delta h Frobenius norm will be bigger or equal to epsilon. So this difference between the eigenvalues will be bigger or same to epsilon with the probability of this constant when k is 1. So the lambda quantity is low bound by 1/3 times 9 to the minus k. So we proved that just by changing that lambda quantity into a distribution and by using some PG inequality and some hypercontractivity theorem. Yeah. Those are the two main components that we used. And yeah, we can low bound this quantity. So let's go back to our Bell sampling procedure. So the probability of the identity coming from the Bell sampling procedure was written as this, and this could have been represented as the average of the cosine of the difference of the eigenvalues multiplied by t. And so this required us to low bound this lambda quantity. And if this is low bounded, then we can randomly select t, and we can get a guarantee that it is 4 from 1 by some constant. Yeah. The important thing is that we transformed this problem into a distribution problem, and we use some PG inequalities and some Bonami types inequality, which is called as the hypercontractivity in the quantum setting. So let's just summarize the algorithm of certifying the Hamiltonians in the real-time evolution setting. So first, by using product formulas, which are called as totalization, we can approximate the time evolution of the delta H. Then we can pick a random coordinate time t from that interval, and then we can get the estimate of the identity probability of Bell sampling by just using Bell sampling. And then if the identity probability is 4 from 1 noticeably, then we can output 4. And if it's close from 1, yeah, we can just output close. Yeah, previously I just explained the intolerant part. So in that setting, it would be 4 and equal, but just by using some simple calculations, such as the Duhamel integral formula, which you can check in the paper, we can discriminate the for case and the close case by using the same method. So yeah, we can just Bell sample from the time evolution of delta H, and we can certify the Hamiltonian. So if we calculate it, the total evolution time becomes like this. So if k is a constant, yeah, this will be 1/epsilon. So we achieved our goal. So this is the real-time access dynamics part. And if you have any questions, feel free to ask. If not, I will move to the Gibbs state part. Okay, so now let me just move. And for last, there's some future works that I would like people to get interested in. So first is we only achieved optimal certification for general K. So can we obtain tight upper and lower bounds for all K? Yeah, it could. I think it would be very hard, but it's an interesting subject. And next is testing the sparsity and the locality of the Hamiltonians. Sadly, there are no efficient or optimal algorithms for testing the sparsity or locality. As you can see in this work, we also just assume that we know the locality, but actually we don't know the locality of the Hamiltonians. We can just assume that it is constant. It's physically relevant to assume that it is a constant, but we cannot know the exact locality. And to use our algorithms, we need the exact locality. So testing the locality is quite important, but the best known locality testing algorithm is 1/epsilon to the 2.5, maybe. It's not that efficient, but there's many people believe that we can do it in 1/epsilon, but there's no known algorithm. So I'm kind of researching it, but I'm kind of busy, and I hope other people can do it. Yeah. So those are the future directions. So let's move on to the Gibbs state learning and certification procedure. So as said, previous Gibbs state method tried the hard route, which is learning the Hamiltonian from the Gibbs state copies, but there is a known low bound that the required number of samples are exponential in terms of beta, which is the inverse temperature, and which could be very large in many settings. So it's not efficient even in the number of samples. So in our work, we just try to
Sorry.
yeah.
Can I, sorry for the interruption, but these exponential lower bounds, are they recent works or are they like old, well-established fact? I haven't worked in this area, so I don't really know what it is.
Yeah, there are some recent results. Yeah.
Oh,
Yeah.
cool.
Please refer it to our paper. We summarize it so you can check it. Yeah. Yeah. Thanks for the question. And yeah, as said, by just learning or certifying the Gibbs state itself, it only requires polynomial number of samples, and when certifying it, it is time efficient. Yeah, I'm going to explain why learning is time inefficient and certification is time efficient. That one is one of the most important intuition and ideas in this talk. So we can emphasize that certification is much more efficient than learning. So if we can if certification is enough in some task, so it is better to just use certification, not to learn the whole Gibbs state itself. So that's one of the main messages in this talk. So as said, on other papers, just try to learn the Hamiltonian using the Gibbs state copies. I kind of made a slide as the bad route, but it's not actually bad, but yeah, it's bad in terms of the sample complexity, so we can say it's bad. We're kind of just taking the alternate route just to make the sample complexity polynomial. So yeah, as said, we are learning the Gibbs state directly, which the most important inequality that we use is described below, where our goal is to learn the Gibbs state in the trace norm, and this trace norm is upper bounded by this formula, which is very important. So what are we going to do? In order to bound this trace norm, we can just bound this formula, which can be obtained by estimating this. estimating the trace of the Gibbs state multiplied by the delta H. So we're going to do it. And how are we going to do it? We want the sample complexity to be efficient, right? So, and we can interpret that this is some quantity that that can be represented as, we can just think that delta H as an observer and the Gibbs state as a state. So we can just take measurements of the Gibbs state by the delta H, and we can obtain this quantity. We can think as that. So we're gonna build a finite candidate of possible normal states, which is the Gibbs state, and measure many simple local Pauli measurements from the copy of the Gibbs state, and use those measurement outcomes to learn or certify the Gibbs state. And I'm going to elaborate it later, but the important thing is to use the copies of the Gibbs state and make many candidates. And from the candidates, we're going to choose the candidates of the measurements, and we're going to use Pauli measurements. And using that measurement outcome, we can construct the Gibbs state reversely or certify it. Yeah. So the first tool is to use the epsilon net. It's important because, as said, we're going to search the possible Gibbs states from the given Gibbs state copies. But the set of possible Gibbs states are continuous, so it is infinite. There are infinitely many Gibbs states that are possible with the given Gibbs state. So there are infinitely many, so we need to make it finite. So we're going to use the epsilon net to try to make the candidates as small as possible. So yeah, we can build a candidate set by using the epsilon net, and yeah, that's one of the tools that we will going to use. I'm going to explain it later more mathematically. And the second one is the classical shadows. Some of you might notice it when I said we need to do many measurements and some Pauli measurements. If we have known O1 through OM, and we want to know all the expectation values, classical shadows let us only use logarithm number of samples when we want to know O1 through OM. So this is the reason why learning takes efficient number of samples with polynomial number of samples, but inefficient time complexity. Yeah, it's directly from the classical shadows. So as said, as you can see in this relation, we need to, if we can bound this quantity, we can bound the trace norm. So we're gonna search the candidates of the possible H prime from the epsilon nets. So, and in that searching procedure, we need to know which candidates are good or bad. So we need to get this estimate. So we're going to set the observable as difference between Hi and Hj, which are the candidates. And by using classical shadows, we can sample efficiently get the measurement outcomes. And we're going to compare the expectation values of the outcomes of the classical shadows. So And as said, we're going to make candidates from the epsilon net, and yeah, it's kind of complex, but we can just use these parameters to set the epsilon net, which have many candidates. But since classical shadows allows us to only use logarithms of the number of observables that we want, it becomes efficient. But yeah, it's not time efficient. Yeah, by using classical shadows, we can estimate these quantities, and by using these quantities, we can set some scores of the candidate itself. So we can just choose the minimum score candidate and say that's the Gibbs state that we want. Yeah, this is the learning procedure. Yeah. So yeah, just by searching all the candidates in the epsilon net and by using classical shadows, we get that this number of samples are sufficient. So the sample complexity is polynomial, but yeah, searching all the candidates by classical shadows are not time efficient. And this does not contract the lower bound that I said. Of course, we do not learn the accurate H. We just trying to learn the Gibbs state itself from many candidates. So it does not contradict the lower bound. And for certification, you might have noticed that we have a given H0. So we do not have to search all the candidates. We just have to have a guarantee that it's far or close. So by using the relation that we use in the learning algorithms, we can get this result. If the Gibbs states are far from 2 times epsilon, we can get a guarantee by for some Pauli observable, the measurement outcome from each Gibbs state are far from this quantity, which is polynomial in beta and polynomial in n if the locality k is constant. Yeah, we can get this guarantee. So we can just repeat the Pauli measurements and check whether the Pauli measurements are close or far. We do not have to set a candidate set and search all of it, since we have the answer Hamiltonian H0 and the answer Gibbs state. So yeah, certification is time efficient in that sense. So let me just tell you the algorithm once more. We can use classical shadows on the copies of rho, and by using Pauli measurements and just by comparing them, whether they're far or close, we can certify the Gibbs state itself. So the sample complexity becomes this, and the classical runtime becomes polynomial in terms of beta and the number of qubits. So these are the results in the Gibbs state certification and the learning task. So now onto the future directions. Can we learn the Gibbs state itself time efficiently, or maybe prove that it is impossible? I believe that is impossible, so there's going to be a lower bound, but yeah, it's not proven to my best knowledge. And second is that in the Gibbs state learning procedure that we used, we need to have a not learning, it's a typo in the certification. We need to have a copy of rho of the Gibbs state of the answer Hamiltonian H0, which is an assumption that is not that practical, because often we try to do certification whenever the implement or the outcome of the algorithm is correct and correctly implemented as intended. But so having the access of the copy of the answer Gibbs state is not that practical. So can we remove the requirement of the access of the original Gibbs state for certification? This could be an interesting direction. And for last, I heard that it's a topic from many PhD students in Caltech. Can we learn the inverse temperature beta from the copies of the Gibbs state and assume that we have a description of H? There are no known algorithms for learning the inverse temperature beta from the Gibbs state, even if we have this description of H. If we don't have the description of H, it's kind of impossible to learn the temperature beta in an efficient way. But even if we have the description of the H and the Gibbs state itself, it's kind of hard to learn the inverse temperature. It is not known, so it could be an interesting topic. So those are the future directions. And just for takeaway, we showed that for k-local Hamiltonians, by using the real-time dynamics, we can certify the Hamiltonians in the Heisenberg setting. And for a constant k, this is optimal in the total evolution time. And for Gibbs states, direct Gibbs state learning and certification avoids the exponential barrier in the temperature, and we can achieve sample efficient algorithms for learning and sample and time efficient learning for certification. So one of the main messages of this talk is that certification can be much more efficient than learning Hamiltonian. So if certification is sufficient in some task, we shouldn't use learning. It's sufficient for only learning certification because it's much more efficient than learning. It's one of the main message. So it's the takeaway. Thank you for listening, and if you have any questions, feel free to ask.